Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4, and we are focusing on chapter 12, Salinity and Ionic composition of inland waters. And yesterday, where we left it at, was at this section, which is control mechanisms on salinity. The variation in ionic composition in the world's inland waters has led limnologists to try to find commonality among the diversity of systems. The Gibbs model is perhaps the most well-known and delineates the roles of rock weathering, atmospheric precipitation, and the evaporation precipitation process on the mass ratios of sodium, calcium, and chloride and bicarbonate versus salinity or TDS. Revisions of Gibbs' original boomerang diagram have expanded the envelope to include a wider range of possible ionic compositions, including dilute lakes that Gibbs eloquently described as crystalline bowls that simply catch rainwater. While there have been many documented departures from the boomerang, the Gibbs diagram has not been displaced in Limnology textbook, as its characterizations hold true for many surface waters. Waters at the rock-dominated end of the spectrum are rich in calcium and bicarbonate and are more or less in equilibrium with materials of their drainage basins. Positions within this grouping depend on the climate, basin relief, and particularly the composition of the rock material in the basin. The chemical composition of low salinity waters, typically dominated by sodium and chloride, are influenced by dissolved salts derived from atmospheric precipitation acquired from the ocean. These freshwaters are limited to immediate maritime coastal regions. In very chemically dilute inland lakes with a strong precipitation dominance and little marine influence, appreciable sodium can be derived from weathering. The major ionic composition of these lakes can fall outside the primary envelope. Inland tropical humid areas of South America and Africa generally have high rainfall with an ionic composition that is either influenced primarily by terrestrial biological emissions and particulate dust or rapid intense rock weathering. Killam showed that plotting data from African lakes resulted in an alchemist's retort than a boomerang. In the upper right of the boomerang, surface water salinity is further influenced by the evaporation and sedimentation of mineral salts. Surface waters typically extend in a series from calcium and bicarbonate-rich low salinity waters of rock dominance to sodium-dominated high salinity waters. Lakes at the extreme saline end of this series are generally located in arid regions and display a wide range of ionic compositions. The examples discussed above represent average concentration and general distribution on a global basis. Where the Gibbs diagram falls short is recognizing the inherent variability in river and lake water chemistry as concentration continually fluctuate in time due to the interplay of solute inputs, precipitation, evaporation, and human influences. Within regions, the distribution of salinity of inland waters is highly variable and localized. Hence, some areas or lake districts have because of uniform rock formation, ionic proportions that are relatively consistent. In contrast, in some areas such as in southwestern Michigan, extremely saltwater seepage lakes may be found immediately adjacent to very hard water calcareous lakes because of complex varying patterns in the deposition of glacial till. Any concept of average river or lake chemistry is useful for scaling global elemental cycling, although not particularly applicable for studies of individual systems. The most comprehensive estimate of the global mean salinity of river water is 128 milligrams per liter based on 1,200 pristine and sub-pristine basins, a concentration remarkably close to Livingston's estimate of 120 milligrams per liter, with rivers spanning a range of 4.7 to 3,314 milligrams per liter. In a randomly stratified sampling of United States rivers and lakes, mean specific conductance in 2,261 rivers was 629 microsiemens per centimeters. The dissolved composition of rivers is dominated by bicarbonate and calcium, followed by sulfate and magnesium and sodium. Over large regions of the temperate zone, the ionic composition of lakes tends to mirror rivers, with dominance by calcium and bicarbonate ions. So before we move on, let's look a little bit at these tables here. So this is the global average chemical composition in milliequivalents per liter, except as noted, of unpolluted rivers and variation in composition according to drainage from dominant rock type. So global average, and so this is of unpolluted rivers, so we're only dealing with rivers here. And so we have the microequivalents and then the milligrams per liter. And what we see is it's dominated by a fair amount by sulfates, pretty high concentration, and silicon dioxide, and then calcium. And then in terms of the contribution of the various rock types, for example, carbonate rocks, of course, contributes a lot of bicarbonates, that makes sense, as well as calcium, makes sense. Like, for example, let's look at sandstone. Sandstone, like it contributes pretty much to about everything except for chloride. Volcanic rocks has a high contribution in bicarbonate, as well as calcium and magnesium, and also silicon dioxide. And then your plutonic rocks like granite and gneiss, it's also pretty good proportion, like proportionated. So we have bicarbonate once again leading, as well as silicon dioxides and the likes. So let's make sure we didn't miss any figures. I think we already went through those figures yesterday. All right, so then table 12-4, and this is the median composition of the river waters of the world, milligrams per liter. The world spatial median values are derived from the PRISRI data set, okay? So this gives you like the median composition in terms of ionic composition of the rivers, of the world water rivers. So world spatial median, so it's dominated by bicarbonate, sulfate, which we already did see that. The 99 quantile, which means that 99% of the samples falls within that, with this kind of concentration, and that's kind of the same what you expect here. Okay, then let's see here, figure 12.3. The prevalence of cations in a randomly stratified sampling of United States rivers and lakes in 2012 and 2013, shown in both milligrams per liter and milliequivalent per liter. So, U.S. rivers. So the sample size is 2261, as just read. And so on the y-axis we have percentage, and then on the x-axis we have the ionic compositions, and it's in milligrams per liter. And then below that we have milliequivalents per liter. And then these are the lakes. So the lakes, we have a smaller sample size. We have 1,230 lakes sampled. So what we see here is, so when it's red, that means it's calcium that is greater than magnesium, that is greater than sodium, than potassium. So for both rivers and lakes, that is the case. And then a second set of rivers is where calcium is greater than sodium, greater than magnesium, greater than potassium. And so we have somewhat of the same kind of distribution between the rivers and the lakes for the reds, the orange, and the blues. I mean, it's not proportionally exactly the same, but with the same kind of like distribution per se, like the same type of family. And then, but it's kind of like it's a little different for this data set here, for the yellow data set, where, for example, in the rivers we don't have much blue, which is the other. So we have a fair amount of lakes that do not fall within this gradient of ions. And then the rivers are really dominated by the sodium, calcium, magnesium, and potassium, not as much for the lakes. And as for the green, It's the reverse, so it's more common for the lakes than it is for the rivers, where sodium, magnesium, calcium, and potassium are dominating. Table 12-5, so the mean ionic salinity in equivalent percentages of several inland waters. So here we are looking at inland waters across the world, it appears, because we have lakes or rivers in Sweden. And then we have the average river content of the world here. And so, as we saw, we have dominance of calcium. Actually, they didn't tabulate, which is interesting. We don't have bicarbonate in here. We have the carbonates, however. And so we have domination of carbonates and bicarbonate here. And like Wisconsin, soft waters, kind of the same distribution. So is there anything kind of a little different that jumps at us? Like the Herbert Brook in New Hampshire is dominated by sodium, for example, more than it is by calcium. The Ugandan River, so this is a tropical-based river. And we have kind of an even distribution except for the carbonates. Otherwise, the concentration is about the same. Okay. So we kind of went over that. So why don't we go into section 2 here. Sources of ions. The salinity of inland waters of the world is highly variable and depends upon ionic influences of drainage and exchange from the surrounding land and groundwater, atmospheric sources, and human activity. In lakes, more so than in rivers, salinity is further influenced by evaporation, biotic and abiotic losses from the water column, and equilibrium in exchange with sediments. In addition, there are many coastal lakes and ponds of marine origin where ionic compositions has evolved from trapped seawater, weathering of soil and rock. The composition of soil and rock and their ion exchange capacity influence both rates of weathering and ion supply to runoff and groundwater. 4 general processes of weathering control ion supply. Chemical weathering from the dissociation of carbonic acid. So I'll let you review this equation. Ordinary solution, not involving hydrolysis or acid weathering, is primarily important in sedimentary deposits rich in soluble salts. Oxidation and reduction processes primarily affect iron, manganese, sulfur, nitrogen, phosphorus, and carbon compounds in soils. Certain soluble organic molecules in soils can bind ions, especially metals, such as iron and manganese, thereby inhibiting these ions from reacting with others. Overall, the absorption and release of ions is dependent upon the cationic availability, the ionic concentration and proportion in a soil solution or leaching water, the nature and number of exchange sites on the exchange complex of soil particles, and the volume of water in contact with the exchange complex. Soil particles are generally negatively charged, with the amount of charge dependent on soil characteristics. The cation exchange capacity of soil is a measure of the magnitude of negative charge. Soils with high CEC can more readily bind positively charged, so CEC is the cation exchange capacity, more easily readily bind positively charged cations, thereby slowing their movement through soils. And ions are more mobile apart from phosphate that is readily absorbed to soil particles. The exchange of ions between soils and the soil solution is highly variable and is governed by exchange equilibria between hydrogen ions and ions attached to the soil particle. So hydrogen ions, I think what we're talking about is protons. It's what drives acidity. Along with ion supply, the depth and mode of water percolation through soil will influence the loading of ions to natural waters. Lakes receiving a relatively large amount of surface runoff are usually very dilute in comparison to lakes that drain deeper soil horizons because the salinity of groundwater is generally much higher than that of surface runoff. Atmospheric precipitation and fallout. Atmospheric deposition can be a significant source of salinity for many dilute freshwaters and for some saline lakes. The delivery of ions from the atmosphere to catchments is largely through wet deposition, the washing out of atmospheric gases or aerosol by rain, snow, or fog. In arid regions, dry deposition of salts can occur in significant quantities and often exceeds wet deposition. All of the major ions and anions in natural waters are cycled in part through the atmosphere as gases as well as in dissolved and particulate form. The traditional suite of ions measured in wet deposition is slightly different from those measured in surface waters because of the low salinity and low pH of rain, protons or hydrogen ions, and nitrogen species, ammonium and nitrate, can account for an appreciable percent of total salinity in rainwater. Variation in atmospheric ion loading to surface waters is significant. Globally, most precipitation has a salinity less than 3 milligrams per liter. Higher salinities up to 30 milligrams per liter are found near the coast and downwind of industrial pollution. The ocean is a major source of atmospheric sodium, chloride, magnesium, and sulfate. Sea spray carries large amounts of seawater into the atmosphere that, on evaporation, forms salt particles that can act as nuclei for cloud and raindrop condensation. Atmospheric salinity can be carried for great distances, although most atmospheric salinity is precipitated with rainfall in the coastal region. Decreasing amounts are carried inland because deposition occurs. Ignoring protons, which can be the dominant cations in many locations, ionic composition of coastal wet deposition tends to follow sodium, ammonium, magnesium, calcium, potassium, and chloride, and then chloride, sulfate, nitrate, and bicarbonates. The effect of atmospheric transport of ions can be seen in lakes enriched with sodium and chloride in coastal maritime regions. Continental rain generally contains less sea salt derived iron and tends to follow the ammonium, calcium, sodium, and sodium looks like it's about the same as magnesium, potassium, and then for the anions, sulfate, nitrate, chloride, and bicarbonates. So you would have to compare, this is the composition of coastal wet deposition, and this is the composition of continental wet deposition. So from the get-go, what we see is dominated by sodium for the coastal, and then dominated by ammonium for the continental. And I'm not sure if ammonium is derived from human input or if it's just natural ammonium. It's a kind of puzzle, probably human input, but we'll see. Wind-blown dust from the soil also contributes salts, especially calcium and potassium, to surface waters. Wind-transported salt from salt pans in arid regions such as in Russia, Western Australia, or the United States can be moved large distances to drainage basins of other rivers and lake systems. So, figure 12-4, distribution of salinity of atmospheric precipitation in coastal and non-coastal sites calculated from wet deposition observation from 2005 to 2007. Breakdown of ionic composition at B, continental sites, including C, zoom in on North America, and D, coastal site. Okay, so let's break this down a little bit. So A is distribution of salinity of atmospheric precipitation in coastal and non-coastal sites, calculated from wet deposition. So this is coastal and non-coastal sites for 485 sites, and I'm not sure where that is. If it's U.S. coast or I'm not sure. Here we have Asia, Europe, and North America, so it's probably global, I would think, but I'm not sure. So what we see, so y-axis we have the number of samples, and then we have the salinity. So coastal, so we have no and yes. Distribution of salinity, no, and from wet deposition, breakdown composition. Okay, so no and yes. So not sure what that means exactly here. Coastal, yes and no. Salinity, so at the end of the day, we see pretty low salinity. I mean, remember, we are for acidic purposes, drinking water is set at 500 milligrams per liter, and for saline waters it's 3,000. So here probably we have right at the boundary, maybe this is 5,000, so maybe 3,000 is right here. So a lot of the waters, even though they're close to the coast, they are not super saline. All right, so then here we have ions, microequivalent. So then we have a color code here. of the different ions. And so in Asia, we have a lot of the sites are dominated by calcium. In Europe, we have it. Europe is pretty evenly distributed. In North America, definitely we don't have very high salinity of these lakes here. And then this is the continental sites. And then here on C, we zoom in North America. So C is this graph, but zoomed in. And so here we are seeing that in North America, despite not very high salinity, we see the highest saline lakes in Asia. We have a lot of the sites that are dominated by it looks like ammonium, so a fair amount of continental sites. Then we have like acidic lakes, we have protons here, and then we're back with our calcium and sodium. And as we were reading in the text, sodium and chloride are coastal-based sites. And then D are coastal sites, so coastal sites throughout the world. So Asia, Europe, North America, Africa, and probably Oceania. And so here we are seeing that a lot of it, as we were reading, is it's going to be sodium, and then also, of course, it's going to be your chloride, so the green. So pretty much expected. This is what we are looking at, and pretty good diagram. And then here, this is figure 12-5, atmospheric deposition rates of sea salts. And so for A, and then B, sulfur from 2001, ensemble mean model by the Task Force on Hemispheric Transport of Atmospheric Pollutants. So this is sea salt, this is sodium chloride, and then this is sulfur, okay? Probably sulfate, I guess. So we have actually, what is surprising, we have a lot of, like in the southern hemisphere where there's just no land, with a fair amount of deposition from sea salt on the water itself. And then probably a fair amount of the lakes actually in Patagonia seem to be like right in that type of current. And then interestingly enough, like the Aleutians and then southern Alaska and the Gulf of Alaska has also pretty good amount of sea salt here, deposition. And then it reflected also as well as in the Far East over in Japan, as well as the Kamchatka Peninsula here. And then here also as well, south of Greenland and Iceland. And then for sulfur, it's a little bit more muted. So sulfur, we're seeing like fair amount of sulfate deposition here in the Great Lakes region, as well as here in the central part of Europe. And then here also as well in China, central, continental China. So that might also be due to anthropogenic sources, I would think, because those are major industrial areas of the world. So I think that's going to be about it for today, and we'll pick it up tomorrow with anthropogenic sources. Thank you for attending today's session, and we'll talk to you tomorrow. Bye.